Can you stand close? Maybe if you are switching the slides.
Yes. Right, so that I'm still in view.
Yes.
Yeah, that's fine.
Okay.
I can move from here to here.
Okay.
It's my area.
Yeah. I can also bring something to put your computer.
Dames en heren, ladies and gentlemen, dear colleagues, dear colleagues, hereby formally open this session and I welcome you all to the public defense of Mr. Robin Björklund. Mr. Robin Björklund has presented to the faculty his PhD thesis on the topic radiation mass loss and its effect on massive star evolution, in partial fulfillment of the requirements for the degree of PhD in science, astronomy, and astrophysics. He shall now publicly defend his PhD thesis. Mr. Robin Björklund, you are invited to give a presentation of about 45 minutes about your work. Afterwards, the examination committee will ask questions and discuss your work with you. I now give the floor to Mr. Robin Björklund.
Thank you very much for the introduction. Thank you everyone for being here, either in person or live following. It really means a lot of me for me that I can now be here to present the work that I've been doing for the past 4 years for my PhD. So the topic of my PhD, as I titled it here now, is radiation-driven mass loss and its effect on massive star evolution. So for the first couple of slides, I want to talk about several of these key terms to help explain what this title actually means. So to start off with, I will begin with the first word, which is the star, because we're doing astronomy here. So we're, at least at K11, we're studying stars. So, and in this image, I show probably the most well-known star, which is the sun. And what we in astronomy often do is we compare things to the sun. So, for example, masses, sizes, or how bright they are, we always try to compare this to the sun. For example, the sun has 1 solar mass, but there are stars which have more or less mass than the sun. So what additional word we have in the title is a massive star. So as I show here, there is, aside from our sun, there are more different kinds of stars. So here I list the stars as they are at a certain point in their evolution. So they are burning hydrogen in their core, and we call them on their main sequence lifetime. So, and in this case, we can order them nicely from cool to hot, or from less massive to more massive, or from less bright to more bright. Sadly, not alphabetically in this case. But what we can see here is, I noted the sun with an arrow here. But the stars that I will mostly be focusing on are massive stars. So in this case, these are the O and B type stars, which are, as I mentioned, they are hot, they are massive, and they are very bright, especially as compared to the sun. So this starts from, let's say, 10 solar masses to maybe 100 or a few hundred solar masses of the mass of these types of stars. So why do we want to look at massive stars? Why is the sun not the only most important star that we know? Well, first of all, they can make very pretty pictures for your wallpaper, but they are also important for actual physical reasons. You might have heard the phrase that we are all stardust, and this is true, because most of the elements that we are made out of and that surround us are actually made in stars. And many of these elements are products of massive star evolution, as you can see on this periodic table, where a lot of these elements come either from large stars or are massive stars, or supernovae, which are also the product of massive star evolution. So naturally, we want to know how these stars behave, how they evolve, and how they can create these type of elements that help regulate how the universe evolves. So I mentioned these stars evolve. They don't stay in their state as we see the sun, for example, now. For example, it will also grow to become a giant red star and eventually die as well. And this is the same for massive stars. So they are born from a certain cloud of dust and gas. And this material contracts until we can say that a star is born. So in this case, I show here a massive star or an O star, where, as I mentioned, these stars, they burn hydrogen in their core. This is their fuel, and this is how they spend most of their lives. However, this hydrogen is limited. They don't have an unlimited amount of fuel. So at some point, we will go past this main sequence life and go on to the more final stages. Some of these stars, for example, they go on to be very big, very cool, red supergiants, as we call them. So in this case, in this state, they might burn different elements that can sustain their life. But this, again, does not continue to happen. So until all the elements that it can burn are exhausted, the star will collapse on itself and create a supernova explosion. So these are often very pretty pictures that we can see. And it's these supernova explosions that help expel a lot of material into the surroundings. So, and this then, for example, goes back into a new star formation cycle, where then this new material from this massive star evolution cycle is then reintroduced into the interstellar medium. On the other hand, the dense core that is at the center of this star collapses into on itself to form a black hole. Of course, this picture is very simple and is not so correct in many cases, because there are a lot of evolutionary phases that these stars can go through. One example is, depending on, for example, the mass of the star, maybe not a black hole is left behind, but a neutron star. Or, and which is the case for many of the stars that I will be talking about today, we avoid this red supergiant phase because these stars tend to lose a lot of mass from their surface. And this, in some cases, can create what we call luminous blue variables. They are very much defined by this mass loss. And through this process or different processes, can avoid becoming a red supergiant. And sometimes they end up, instead of being a very cool, very giant star, they become a very stripped and very hot star, which we often call a Wolf-Rayet star. So this then is a different final fate for massive star evolution. So this already is a rather complicated picture of stellar evolution, but the way these stages flow into each other very much depends on how we model them, how we approach the different physics that goes into the stellar structure and evolution of these stars. So I mentioned that these stars lose mass. So one thing that is very common or very well known for these stars is they lose material from their surface through a stellar wind. And this wind is not a wind as we know on Earth. Here it flows horizontally and blows wind in our face. But for these stars, this wind is initiated from around the surface and removes material to infinity, let's say. So in this case, we see that mass actually is transported away from the star, so it gradually loses mass. So how much mass do they lose? So here I put a typical number, which is 10 to the minus 6 solar masses per year. What does this mean? This means that a star with this mass loss rate loses about the mass of the sun in 1 million years. And is this a lot? Well, yes, it's quite a lot. These stars typically don't live as long as the sun because they shine much more brightly. They use their fuel a lot quicker. So instead of like 10 billion years that the sun would live, these stars live, let's say, 10 to 20 million years. So I added to this calculation to see how much mass they would lose over their entire lifetime if they would lose mass at this rate. So for example, for 20 million years, we see that the star loses 20 solar masses of material from its surface. And this can be a very significant fraction. And this is definitely something that impacts both the life and the death of the star, which would create the supernova and either black holes or neutron stars. So it's this mass loss that is also one of the terms in the title that we want to characterize for these massive stars. Now, why do these stars lose mass? Now I added an extra term to this from the title, which is radiation-driven mass loss. Because these stars, they are very hot and they are very bright. This means that there is a lot of radiation coming from the star. And in the atmosphere, we have a lot of gas. It's very hot, so this gas is ionized. So we have a lot of different particles, as I show a couple of them here on the slides. And this radiation interacts with the gas of the atmosphere. So typically, of course, you have the gravity of the star. It's very massive, so the particles are typically held to the star through its gravity. But for these particles, they also experience a force from gravity, from radiation. So this radiation can either be scattered or absorbed by these elements. And in doing so, they gain the energy from this radiation, but also momentum is transferred. This means that because the radiation is coming from the bottom, this means that the velocity of your material will go outwards. And in this sense, for these hot massive stars, this means that we can create a very efficient wind outflow, which carries mass away from your star. So now we covered all the important topics of the title. So we have radiation-driven mass loss, and we studied this for massive stars to see how it impacts the evolution. But how do we know all this about their evolution stages, about that stars in fact have winds, these massive stars? Well, of course, we also can do observations and try to test these observations with simulations that we have. So this is a typical duality of astronomy, that we both have our observations and our simulations. Now, for today, we can choose to follow two of these topics. So on the one hand, we could take the red pill and look at observations and just derive, let's say, our quantities using the models as a black box. Or we can choose to take the blue pill, where we dive into the machines, which are our simulations and models, and try to figure out what is happening on a theoretical, on a model level at these stars. So this is exactly what we are going to do today, is we are going to dive into this matrix of these stellar winds. So now I come to the more concrete goals of the thesis. So what I want to do is to predict mass loss rate using these models of the atmosphere and the wind. And these models, they simulate the interaction between this matter and the radiation. If we can calculate how this interaction happens, we know how much material is lost from the star. These predictions we can then do for many different models. So we can set up many fake stars, predict the mass loss rates for them, and see how the mass loss behaves. If a star is larger or smaller, or if it's brighter or less bright, does the mass loss rate go up or down? This we can do if we study many stars. We can see the behavior of these mass loss rates with these kind of stellar parameters. And if we know how this mass loss behaves, we can then feed that back into the stellar evolution. Because I mentioned mass loss for these massive stars is important to take into account into the evolution models. So in this case, if we can predict, theoretically predict our mass loss rates, we can then implement them into our evolution models and see how actually our different evolution stages are affected. Do we get a red supergiant, or do we get this very compact stripped star? This often depends on, for example, the mass loss that we assume in our models. So I will go more into how this interaction works, how we will set up our atmosphere and winds. So what we see from these winds often are the stellar spectra. How are these spectra created? Well, you have some sort of source of light, which comes from the center of your star. And this light then passes the gas, your ionized gas, from your atmosphere. Here depicted by this cloud of gas. And because there is interaction, it will affect the spectrum. What is this spectrum? Well, here it's depicted by a rainbow, and which is very accurate because when the light of the sun, for example, passes through a prism or through a raindrop, we can actually see a rainbow because this light is comprised of lots of different colors, lots of different energies or wavelengths, as we would call them. But if we would look closer at this rainbow, we would, for example, see, as we see here, some darker bands at certain colors, which means at certain wavelengths or energies. And this is exactly because of the interaction of the radiation with the gas in this cloud of gas, because they absorb or scatter this light at certain frequencies or certain wavelengths, which means that we get these darker spectral lines, as we call them. Now, what affects these spectral lines and how they look? Well, it depends on the specifications of your gas. So first of all, it depends on what type of chemical elements you have in there and how much of each of these elements are present. And second, of course, there's a lot of different physical properties of your gas. They can have a certain velocity, a certain temperature, a certain density, and so on. And all these will affect how your spectrum looks like. And in this sense, we can see that we model how this atmosphere looks like, what the temperatures are, how much material there is. And we can compare them to the observations, which are these rainbow-like spectra. And in this sense, we can learn something from our observations to see how it matches our physical setup of our model. Now, I use these models not to directly compare to observations. However, I use the models to set up the atmosphere and wind of massive stars and try to predict the mass loss rates belonging to a certain fake star, as we would call them. And in this case, this loop of radiation and matter is very important because this radiation interacts with your material, but on the other hand, your material affects the way your radiation behaves. So this is a very computationally intensive loop that's very notorious. And this is something we have to calculate in order to find the way that radiation behaves and the way that the winds and the atmospheres are structured of these massive stars. So what do we need? We need a certain input. So for the input, we have the stellar parameters of our star. And in this case, we look at the mass, the radius, the luminosity, which is just the brightness of your star, its surface temperature, and its composition. And these help build up a model which define your star, basically. Another thing we need is we need already initial guess of how the structure looks like of the atmosphere or wind. We need a guess of the mass loss rate because we already need to be able to calculate this transport of radiation through the material. After this first step, we then go through this loop where the radiation affects the matter and vice versa until we get a solution that converges. So between different iterations of this loop, your solution doesn't vary a lot anymore. And then we can say that we find the structure of our winds. And as an output then, we can get our mass loss rate, our theoretically predicted mass loss rates for our stars, as well as different structures, for example, the velocity, how the material is accelerated from the surface to infinity. And we can also get these synthetic spectra. So this plot is the same as this rainbow plot I showed before, where then instead of the darker lines, I show here dips in the brightness, which are the spectral lines of your star. So this is what we get from our atmosphere modeling, where important for the research that I did for my PhD is mainly this mass loss rates. So connected to these stellar parameters for this fake star, we get how much mass it loses in a certain time. So what we can do with this, so we can set up many models of many fake stars to see how the mass loss rate behaves. So I mentioned we need our input model, or input model needs some stellar variables, which are our luminosity, our mass, our temperature, and I call it here the metallicity, which is just the composition of your material in the atmosphere of the star. So if we construct many of these models and predict the mass loss rate, we can see actually how the mass loss rate behaves. And I show the extent of this grid on this simple plot. So for astronomers, this is a quite intuitive plot. This is the so-called Hertzsprung-Russell diagram, where we have where we show the temperature of the star and the luminosity of the star. But for the purpose of here, I just want to show you that we have a very extended grid where we cover a lot of different temperatures, surface temperatures of the stars, and a lot of different brightnesses. And for each of these points, there's also different masses and metallicities or chemical composition. So these grid points cover a lot of the evolutionary stages of these hot massive stars. And for each of these points, we then get a mass loss rate associated with it. And this is done through a big grid of these models. And from this, we get the main result that we have our mass loss rate depending on these stellar parameters, our luminosity, mass, temperature, and composition. So what can we do with this? We can, for example, make a recipe out of this grid. So what do you need for this recipe? You need the ingredients. These are, again, the same stellar parameters as are varied in the grid that I showed before. So these stellar parameters are then fed into the recipe to calculate the mass loss rate. And this recipe is basically a boiled down version of all the results within the grid. So this is a simple calculation, then basically only depending on these parameters that are our ingredients. And then as a result of this recipe, we get a mass loss rate of any hot massive star that we want. So now that we have this recipe, we can try to compare this to other mass loss rates. So far in our models, we have only looked at calculations and theoretical predictions of the atmosphere and the wind, but we don't know yet if these mass loss rates that we get from them are actually realistic. So in this plot, I show a comparison of predicted mass loss rates from our recipe then to some observed values. So in this case, we can see the mass loss rates for a different range of stars where they are ordered by their brightness. And well, you might see these markers, they don't match exactly at each point. But the point is that the scatter for both of them are at the same order of magnitude. So we see that the mass loss rates that we predict fall in the same order of magnitude, the same size of mass loss as the observed mass loss rate. So this is a good confirmation that we are predicting, let's say, realistic mass loss rates. Now, also other recipes exist. One example of this recipe is the recipe by Vink et al., which is, I show this comparison because this recipe is used a lot in stellar evolution modeling so far. So the point with this recipe is that often they have been found to overestimate the mass loss rate compared to observations such as the ones that I showed on the previous slides. But if we show here now a direct comparison of our recipe with this previously used recipe, we can see that our rates are consistently below the previously used massless rates. So this, I show just a sequence for different temperatures. What is the massless rate we can predict, in this case for a star that is 50 times the mass of the sun. So, and we see that for these two recipes, we get actually two different results. For at the hotter regime, we see that this is what we call the O-star regime. We see that on average, the massless rates are about a factor 2 or 3 lower than the ones previously predicted. However, maybe more notable is this gap at lower temperatures. So here we can see that there's a big difference of 10 to 100 in factor between the different massless rates. And to understand this, I need to introduce the concept of the bistability region. So I go back to this plot of before, where we have the interaction between our radiation and our material. I mentioned that this material, this is ionized gas. So our material is in a certain ionization state. And this stage is dependent on the temperature and the densities that are present in the gas. And important here is that different ions of the same element actually interact differently with radiation. So now the bistability region is a region at around 20 to 25,000 Kelvin, or the most notable one at least, where it is known that some elements in the wind, some elements that are important to drive this outflow, change their ionization state, such as iron. And this then can affect the way that your radiation interacts with the material. Now, what happens for our different recipes? Now, when we go to these lower temperatures that I showed before, for the previously used recipe, they predict a very big jump in the massless, that the massless rate would go up by a large factor. However, in our detailed modeling of our radiation with our matter, we find that our massless just keeps on decreasing when we go to these lower temperatures. So this is an important result, that we seem to find no bistability jump in our massless rates for these stars. So now that we have our predictions, now that we have a recipe of our stars, we can try to see how this impacts the evolution of this complicated evolution diagram that I showed before. Because as I mentioned, mass loss in a lot of these stages holds a very important role in determining which evolutionary stages your massive star goes through. So these evolution models take into account a lot of physics. We need to introduce a physics which is then computed throughout the life of our star. So here I mention several important physical concepts which are often big uncertainties that can influence the evolution of our massive star. So for example, our stars rotate as well. This can introduce a lot of internal mixing inside your star. There's also magnetic fields that can affect the way that your star behaves internally, as well as binarity. What is binarity? Well, stars, a lot of massive stars don't live on their own, but they might have a companion or multiple companions. And at some point in their life, they can interact as well. And this, of course, this interaction, they can share material, for example, affects the way that they evolve throughout the rest of their life. However, what I want to do is I will assume that the rest of these physical processes are fixed, and we want to only see what impact does this mass loss have. If we now use our new predictions, which are reduced as to compared to the previous ones, how does this affect the evolution stages of our massive stars? And one of these stages that I mentioned, which is a product of massive star evolution, is the so-called Wolf-Rayet stars. And these stars are hot stripped stars, at least the classical Wolf-Rayet stars. And we now want to know how are these stars, which are the final phases of massive star evolution, how are they affected actually by our mass loss? Well, to create such a Wolf-Rayet star, we need to somehow strip material away from our big massive star that we have in the beginning to the very hot and compact star that we are left with. So this stripping can happen through this wind, because I mentioned these winds take away material from your star. And if we use then the previously standard rates, well, these are very, this has a lot of mass loss. So this means that the envelope, the outer layers of your star can be blown away to create such a compact hot star. If we then implement our newer rates, which are reduced in its mass loss, we seem to have trouble shedding this outer layer because there's not enough time and not enough, the mass loss rates are too low to actually remove the material from the star within the lifetime of this massive star. However, we do observe Wolf-Rayet stars, so they do exist. So we know that somehow they have to be stripped of their outer layers. Well, there are more options except for this wind stripping. For example, I mentioned that a lot of stars, a lot of massive stars live with a companion. And this can also help strip the star, because if these stars are close enough to each other, material can be transferred from one star to another, which means that this one star is only left with its hot, compact core, which is the Wolf-Rayet star. However, there are a lot of observations that might indicate that this binarity may not be enough to explain the amount of Wolf-Rayet stars that we see. One other option, however, to strip away mass from a star is through giant eruptions. So we have seen some giant eruptions which remove a lot of material in a very short amount of time. This example I show here is the star Eta Carina, which lost a couple of solar masses in only a couple of years, which is a lot more than the couple of million years of the example I showed before. So in these type of explosions or eruptions, stars can lose a lot of mass, which can strip your star as well to become a Wolf-Rayet star. One problem, however, with this is that we do not observe many of such kind of eruptions. And according to some, these eruptions are almost always linked to some companion, some binarity as well. One other option to strip your star, which is sadly a bit more boring than giant eruptions, is the input physics of our models. So I mentioned, aside from our mass loss, there's also internal mixing, there's rotation, there's convection, all these things. We kept these fixed throughout our evolution modeling, but perhaps if we look at different types of mixing within the star, it is possible to create, to strip our star, even with our reduced winds. So this is something that requires some more attention to see if, in fact, with our reduced mass loss rates, we can still strip our stars as single stars. So this already brings me to my conclusion. We looked at, so the title of the thesis was Radiation-Driven Mass Loss and its Effect on Massive Star Evolution. So to start this off with, we looked at this radiation-driven mass loss. How does radiation interact with matter? And how can we use this to predict mass loss rates? So we have made a setup to predict mass loss rates of mainly hot and massive stars. And if we can do this for many stars, we saw that we can create a mass loss recipe which then just boils down our results to a very simple dependence on the stellar parameters, which are our luminosity, our mass, and so on. Our results show a nice comparison to observations, because a lot of observations have shown that the previously used or previously predicted mass loss rates over-predicted the mass loss of these stars. So in this case, we see that this nicely connects to what we find from the observations. A further result that I showed is that we do not find a bistability jump. When we go to cooler temperatures, when our ions change their ionization state, we do not see that a lot of mass or a lot of extra mass is driven away from these stars. Now, because we have this, this recipe, it is easy to implement this into evolution codes and study the behavior of mass loss of the mass loss for different evolution stages of massive stars, where in one example we saw that because we have reduced our mass loss, we have trouble creating Wolf-Rayet stars, which are compact stripped stars, with the mass loss that we have. So we need either additional stripping, or we need to look at the models to see how we can create these Wolf-Rayet stars in the first place. So of course, there's a lot of additional work that we can do here. For example, we can look at the mass loss recipe at different stages of our evolution. So our grid covers a certain range of our parameters, but it doesn't cover the entire evolution of massive stars. So there are some evolution phases, for example, of very bright stars, where we do not have our predictions, where maybe if we could create in a similar way as in the PhD work here, our mass loss rates, this could maybe help provide additional mass loss at certain points in the evolution of massive stars. Furthermore, as I mentioned, we need to look at our evolution modeling as well. If we find the missing ingredient, to see how we can strip our Wolf-Rayet stars, if we need to look into the input physics of our models, or if we maybe need to invoke this binarity, these companion stars, to help strip away the material of these stars and still be able to use our predicted rates that we find from our atmosphere modeling. Thank you for your attention.
Thank you, Robin. We are now starting the discussion, but first let me introduce the members of the examination committee. We have Professor Andreas Sander from the University of Heidelberg. Oh. Start from there. Sander from the University of Heidelberg. We have Professor Alex de Koter from the Institute of Astronomy of the KU Leuven and University of Amsterdam. We have Professor Tom van Dorselare from the Institute for Plasma Astrophysics of the KU Leuven, Professor Connie Aerts from the Institute of Astronomy, the KU Leuven, Dr. Andrew Tkachenko from the Institute of Astronomy, and the promoter, Professor John Sundquist from the Institute of Astronomy. And I am Ricardo Raber from the Institute of Nuclear Irradiation Physics of the KU Leuven as well. So we start, as usual, with our external members. So please, Professor Sander, you can ask your question to Robin. Perhaps you can come here so that you can take out your mask. Everybody can follow you.
Thank you very much. Thank you, Robin, for an excellent overview. Let me maybe start with something that you touched upon a bit briefly, but I think it's maybe an important thing you might want to tell us a bit more about. Namely, you talked about that you tried different methodicities of chemical compositions, and you later even mentioned that maybe additional mixing might be something. Maybe you can tell us a bit more about why it's important to actually care about the different elements that are in these winds and why a different composition might make a difference to your prediction.
Yes, so indeed I changed the composition for 3 different types of environments. So first of all, we have the galactic environment, and then also for the Magellanic Clouds, because they have a lower amount of what we call metals, so anything except for hydrogen and helium. And in this case, these winds are driven by the interaction between the radiation and this matter. And if we have a more metal-rich material, there are more atoms that can interact with your radiation, which, as we find in our modeling and as has been shown by other works as well, helps drive a higher mass loss rate. So, and different elements have their own contribution. For example, iron has a lot of these spectral lines, which are used to accelerate your wind. But there are also other elements that are important to drive this wind. And as you mentioned, this mixing can maybe cause different composition than the ones that I use in this PhD thesis. So if you have, for example, an overabundance of carbon, nitrogen, or so on, this might help or this might change your mass loss as compared to the fixed composition that I have used here. So in this sense, this recipe can only be used for this composition because it might have a small effect by changing some of the abundances of some of the elements.
Okay. Yeah, thanks very much. Indeed, that's an important point. So you told us a lot about the mass loss rates that are coming out of the predictions and how that changes compared to previous predictions. What about the actual wind velocities that you get out? I would be very interested. What is the difference to the previous ones? And also, do you see trends there with metallicity? Is that something that's relatively unique? For example, if the mass loss rate always increases, then the velocity decreases, or do you see basically things are all over the place? What are the results from those studies?
Yes, so indeed, aside from our mass loss rate, we also predict the velocity structure and the terminal wind speed, which is an important parameter of these winds. A general trend that we find from our modeling is that our wind speeds are relatively high as compared to what is observed. Also, what is compared to some of the previous models, like the Vink et al. Models, but the recently updated ones, let's say. However, it might not be so problematic that these terminal wind speeds are so high because, well, we are missing some of the physics in our models. So what we predict are maybe not the accurate terminal velocities, but the missing physics could potentially be in this outer wind where it affects the terminal wind speed, but not necessarily the mass loss rate, which we care about here. Then relating to the connection to metallicity, for example, so I studied also to see if this terminal wind speed changes at different metallicity environments, but it seems that the scatter is quite big on these terminal wind speed, on the results. So it seems that it's rather constant with metallicity. So this is what our predictions, what they show.
That's probably a bad news for the observers who are interested in these trends, but that's what you get out. And it's very
yes, yeah, well, yes.
Okay. Thank you.
I think if you stay here, the camera will pick you up and you can maybe here.
Yeah. So, dear candidate, before we exchange thoughts about the topic of your thesis, I first would like to congratulate you. It's a beautiful thesis and it's beautiful research. Even though the topic of your thesis is challenging a theory that 20 years ago we developed in my research group. One of my first PhD students worked in. But that's a good thing. Yeah, I mean, theories in science need to be challenged to check whether they are correct, and it also helps us to further our understanding of, in this particular case, the topic of mass loss. So that's a good thing, and I thank you for that. So my question is about one of the, I lost the page, one of the important things that you discussed, and that is that your predictions are not yet perfect in the sense that if you implement them in these evolution models, you predict stars to be in regions of what you explained is the Hertzsprung-Russell diagram, where we do not see them, and you do not predict them to be in regions where we do see certain types of stars. So there's still work to do, I would say. Okay. So I first have a small question, because I looked at this diagram in your thesis where you show that, of course, in great detail. I noticed that with your predictions, the tracks only very briefly tip the red supergiant branch, and with the predictions based on the Winkelthal recipe, move up during the red supergiant. I just wanted to ask, does it mean that in your predictions you lose less mass in the red supergiant stage than with the Winkelthal predictions?
Yes, but mainly this branch is not necessarily on the red supergiant branch already. So there's sort of this transition temperature where these stars want to turn back, which is, I think, around 10,000 Kelvin. So this is not what we would call a red supergiant yet. It's a bit too hot. Because we have this turn back point, indeed, because the Winkelthal recipe, if we use this recipe, it lives slightly longer on this colder side, but this does not mean that it loses mass as a red supergiant. I think still the mass loss applied from the Winkelthal recipe.
So now to my question. So you explained very carefully that if you just use your recipe as is, you do not predict these Wolf-Rayet stars. But there is another group of stars you do not predict if you simply use your recipe, which is the luminous blue variable stars. Yeah? So both of them you do not predict. And now you just said during your presentation that maybe the luminous blue variables may all be binary stars, potentially.
Yes, so this was related to the topic of eruptions. So I know some experts in the fields like Nathan Smith, they are of the opinion that basically all of these eruptions are a product of binary stars. For example, when they merge, which is also what is thought to have happened to Eta Carina, that they then get injected with energy and then expel their layers that way. So in this sense, of course, we cannot predict this with our single star evolution models. And in this sense, we do not get our luminous blue variables. However, what I'm also missing from the models that I mentioned in the end is the very high luminosity range, because these stars, LBVs, they are very luminous. So perhaps we are missing some physics that is not caught by just extrapolating our recipe into this regime. So maybe here we do have this LBV type of mass loss that we do not indeed not capture in our single in our evolution tracks with our recipe at the moment.
Can I ask one more question? Okay. So, because I was thinking, you know, if all the luminous blue variables are interacting binaries, and the luminous blue variables are the progenitors of all Fourier stars, then maybe it is really so that all of them form through this chain. So my final question is, I'm trying to see whether we can fix things with your recipe anyway. And it's kind of a follow-up on the question of Dr. Sander. What you did not do when you developed your recipe is change the surface helium abundance. If you would do predictions where you do that, which would be a more consistent way of dealing with the evolution, could that could that lead to the formation of luminous blue variables and Fourier stars through the single chain?
Yes, so in fact, we could indeed, if we would introduce also this different helium abundance and different electrons in the ring, then maybe this provides an additional force, an additional mass loss for these stars. However, it's not sure if it's enough even then to strip the stars, because also what we do in our evolution modeling is at a certain point when we get when we want to strip the star and when the abundance start to change on the surface, then we switch to a different type of recipe, which is valid for these hot compact stars. And this is unchanged from my work still. But perhaps if we would then specifically model these stars, then with our setup, I mean, I can't predict if it's enough to strip this last amount of mass from the star. Something for the future.
Thank you for this discussion, and again, congratulations on the beautiful thesis.
Yes, thanks so much.
Thank you. Professor Björklund from the Institute of Astrophysics.
Okay. I think I'm visible on the screen, so let me ask my questions. So let's go beyond your thesis. And you mentioned already on the slides in your presentation that you forgot several aspects in the evolution of stellar winds. For instance, you mentioned rotation of stars, which you didn't include in your modeling. And in your thesis, you also discussed about clumping of winds. And so I'm wondering, could you speculate or discuss a bit how the clumping is influenced by the rotation of these stellar winds?
Yes, so good question. So, in fact, I do include rotation in the stars, but maybe, as Connie, for example, pointed out, this might not be physical. So this can also, on the other hand, affect evolution. So, as how rotation would affect the clumping, I'm not exactly certain on it because how this clumping is initiated is because you have these instabilities in your wind, which are because you have your radiation, which drives your material, and it's very sensitive to a certain resonance zone, as we call it, and this can drive a very strong instability in the wind. Now, if we would add rotation, I guess this would add an additional force acting on the particles, which might, in my intuition, it might help deform or change the shape of your clumps. So perhaps indeed, in this sense, because the clumps look differently, they might act or interact differently with the radiation. So that's a possible. But yes, that's.
And do you expect some asymmetries then in the stellar winds?
Yes. So indeed, rotation helps to create a symmetry compared as the equator compared to the pole. So maybe indeed at the pole there would be less of a centrifugal force, where then the clumps just behave as they would normally. So maybe then the mass loss would be different at the equator. Maybe it's higher at the equator than at the pole. So maybe there would be some asymmetric mass loss because of your introduction of rotation. That's true.
Yes. Let's come to another term you mentioned in the slide where you mentioned the things that you forgot, right? Which is the magnetic field, which is very close to my heart.
Yes.
So you mentioned that these stars have very little magnetic field, which is indeed true, and we can measure that with observations with modern telescopes. But still, the plasma that you have in your stellar wind is very highly ionized, so they must respond to the magnetic field. So can you also speculate what would be the effect of a magnetic field on the structure of a stellar wind, clumping or outflow velocities in different directions?
Yes. So what we know from observations, for example, is some of these massive stars indeed do not show strong magnetic fields, but some of them do. So indeed, for these stars that do show like these large-scale magnetic fields, we see that material is more guided by these field lines to form some sort of structure around, again, around the equator. And this is also observed in, for example, the spectral lines, which, if looked at a different angle, we see a different type of emission or absorption. Important for these stars is because your magnetic field, it sort of traps material, which can then reduce the amount of mass that is eventually or actually lost from the system. So the star will lose its mass through its normal radiation-driven wind, but the magnetic field, if it's strong enough, can still capture some of that material.
How to include that in your models?
How to include that? Well, our models are sadly just one-dimensional, so we cannot include this asymmetric magnetic field. So this would require a lot of adaptation, I'm afraid.
Yes, I agree with that. Yes. So then, this brings me to the next question, where you talk about observations. And I'm wondering, looking at your thesis, in particular figure 3.6, there you show the terminal velocity as a function of luminosity or temperature, because they're related anyway. And it seems that the terminal velocity is higher for less massive stars, but yet also the driving is lower. Does that mean that the driving takes place for a longer time, and that in fact the stellar wind is extending over a longer space? I mean, in space.
Well, yes, it's hard to pinpoint where this comes from, but for these lower mass stars, they have less dense winds, right? So there's less dense material, and this less dense material is, let's say, easier to accelerate to higher terminal wind speed. So in that sense, we find that for these lower temperature, lower mass stars of lower mass loss rates, that we have an effect that the terminal wind speeds go up.
Yeah. And then my main question about this was, is this observable? Can we observe stellar wind bubbles? For instance, in Eta Carinae, as you showed in the picture, it's clear that we see this stellar wind and this eruption. And can we devise a telescope or a filter where we can observe these stellar bubbles? And can we indeed verify that the size of this stellar bubble around low mass stars is larger than the one around big mass stars?
That's a good question. It's not something I really thought about before, because the main observable for these terminal wind speeds that we do look at is at the UV lines, because these UV lines are also formed far away in the wind, basically also at infinity, as we call it. And if we can observe material there, we can see the terminal wind speed anyway. So, but indeed, perhaps because you have faster material, this could relate to larger bubbles. So perhaps it would be interesting to observe also this as compared to the mass of the star.
One more question? Or one more question, the final one this time. So in your last chapter of your thesis, you discuss about the influence of the atmosphere and the wind of the star on the oscillations within the star. But I wonder, can you do in your models the opposite? can you study the influence of oscillations in the star on the wind? And is this observable?
So in fact, indeed, if you have strong pulsations of your star, this motion could impact the way that your material is driven away, because you have different temperatures, different motions of your star. So again, in a one-dimensional model, it's hard, I guess, to actually take into account these pulsations, except in some cases they just use a simple piston model to introduce some force from a pulsation, but this is typically for large radio pulsations. So in that sense, it could be possible to introduce them in the modeling here. But to see if it would actually affect, like in a realistic pulsations of these massive stars, maybe again multi-dimensional models are needed to calculate this interaction.
Yes. Okay. Thank you.
Thank you.
Thank you.
All right. Thank you, Robin, for the very nice talk and for the background. I love this background, and I remember when you were starting a PhD, you were very eager to do computational work. Okay? So I can now not resist to ask a question and challenge something you have written. So I'm going to read a part of your thesis now and then ask my question. You write that in reality, the winds may be structured and these structures may change in time. However, due to computational limitations, it is currently impossible to calculate the structure and radiation in stellar winds in a time-dependent way. Right? Now, all these young people in the crowd, they love computing. Is that really impossible? Because if I now look at the more modern stellar evolution codes, they do also have radiative levitation in the interior, where you have to compute for each frequency, for each time, for each position, the radiative force. Isn't that what you need as well, but then in the wind? So the step then from going to a steady mass loss and a 1D description and all these beautiful insights that you have, isn't that a bit drastic? Couldn't you, is that laziness of the massive star community?
I don't think it's laziness, no. Also, I believe indeed impossible is a strong word to use in that sentence. However, because you have the models that I use only take into account indeed the detailed radiation calculations, which are in these massive stars, or in the winds of these massive stars. They are in itself already intensive, because it has to be done in NLT, so non-local thermodynamic equilibrium. And you have a moving medium, so that your frequencies are not just their frequencies, but you need to take into account their Doppler shift. So in this way, to get our structures, it already takes a day for one time, let's say. So if we would need to look at more dimensions and at more time snapshots, this would add or multiply this day by so many more, such that we get not an impossible way to calculate it, but at the moment not very feasible to do so. So this is, I guess, a step in difficulty, a step more than calculating the radiative levitation inside the star, because there we do have LTE. So there, in that sense, it becomes a lot less computationally intensive. So it's not laziness. No.
I agree that that's a good answer. But still, you have these beautiful grids that you showed so nicely. Huh? Would it be beneficial to just take one star with one mass, one initial chemical composition, and try to have some kind of simulations across several until you have convergence, and then use your structure equations here instead of going into the beautiful relationships that you derive. It would be more consistent, I think. I agree you can't do that for the whole region, but sometimes some stars deserve more attention than others. So has anybody tried this already? Are you aware of any?
So I'm not aware of this, no. But indeed, it would be a possibility instead of just creating a recipe.
Yes.
More tailoring the wind models to the evolution models.
That's
and
right.
connecting them, basically connecting the winds and the interior structure.
That would be more self-consistent, no?
Exactly, yes.
Yes.
So this would be possible, and it was maybe in the beginning of my PhD a potential path for me to go on, but I chose to go this path because in the massive star community, this has more traction.
Oh, I know that. Okay, I accept that answer. Okay, then I want to come back to, I have to care about rotation, and Tom sort of already a little bit asked the question, but let's say that my intuition sometimes goes against the one of all others. And so what we see in stellar interiors is, when you have a fast rotating core, it's harder to get out as a particle. So this goes against the reasoning, like the faster the rotation, the easier it is to escape, right? So what if you have a wind very, very close to your star and a fast rotation there? I could imagine it's just more difficult to fly away. So is that against relationships between mass loss, metallicity, and rotation? Is that known, or is that just not investigated in that way?
I'm not aware. I don't think it's investigated in that way because we always just, as you say, we just think that rotation just enhances the mass loss because you have some centrifugal force that helps, or let's say it lowers your gravity, which helps remove more mass.
Yes, that's because you think in a radial way,
yes.
And I think tangential.
Yes.
That's my thing.
Yes.
Right?
Yes, so I'm not aware of how, if we don't consider just the 1D star, if it would actually be more difficult to accelerate the wind. So that I'm not sure of.
Could you investigate that in some way, or could you think of a path to look at that? Or
so it is possible to introduce some rotation in let's say, 2D or 3D hydrodynamics models where, well, you then again have to take into account the simpler version of radiation, but there are approximations which are often good enough. So in this sense, we could investigate if when we actually have a rotating star, maybe on a large scale where we're just looking at the surface, if this maybe impedes the material from flowing away.
I think there were, like some 20 years ago, were some 2D wind models by this Cruz and Patrons, or what, is that something that your community is looking at? Maybe that's more a question for your supervisor, but I'll ask you. Because that's what I would think would be extremely helpful, because now for interiors, we're doing 2D models. But we're not putting good winds on top of them.
So yes, it's something we are interested in. So we basically we look at adding more things to, like there's people in our groups that add magnetic fields, for example, or yes, that we went but also rotation can be introduced here. So that is something we are interested in, and that can actually be used to investigate in these low-DD models.
Okay. So I think there's still lots to.
Yes.
But there's only so much you can do in reality. So congratulations with graduation.
Thank you.
you.
All right. Congrats, Robin, from my side as well. A very nice piece of work. It was a pleasure to meet. So logically, you would actually expect me to ask questions about binarity, right? And you're wrong. I'll have a couple of very general questions that you triggered in your talk. Okay? So you started with this beautiful introduction of how stars are formed, how they evolve and ultimately die, right? So let's touch upon the birth of stars. Can you try briefly explain what actually determines the mass of the star at Earth? Can the star grow to infinite mass? And if not, if there is a limit, what is actually that limit and what determines that limit?
Okay, yes, good question. Because indeed, the mass of the star is determined often by its birth. So you get your cloud that contracts, but it doesn't all contract just to form the star. There's typically a disk around it from which the star accretes material. So, and important for this is, for example, the metallicity, because if you have a higher metallicity, as we talked about before, you have more wind driving. So for these hot stars, they already lose mass when they are formed. And when they are losing mass, this impacts this disk that they accrete from. So if you have a star that's not void of metals, there will always be a significant amount of radiation that pushes back against your disk, and this is thought to set an upper limit to the mass that can be accreted onto your star, because your disk ablates away, as we would call it. So, and this is often, well, that depends, of course, on many factors, but this is thought to be a few hundred solar masses for these massive stars. But there are stars from much longer ago which are a lot more metal poor, which are thought to be a lot bigger than these 100 solar masses.
Yeah. Thank you for a nice answer. And my second question and last question would be, well, about your work actually. So you told us that you essentially studied an ensemble of fake stars, right? On the other hand, you also showed some real stars for which we do have measurements of the mass loss rates, right? So my question is very simple. In fact, why would you want to predict something when you can actually measure it? So why would I want to predict the length of this table if I can actually go and measure it? What's the purpose of this predictions?
Well, that's a good question. So one point is we do not have an unlimited amount of stars that we can measure to get their mass loss rates, because we need this mass loss rate, for example, in evolution modeling, which can be used to compare to all kinds of observations or all kinds of evolutionary stages. So if we have a certain prediction, we can then theoretically see how this mass loss behaves when we change different stellar parameters. Also, this measuring is not just simply going there and seeing how much mass they lose. They also need a certain modeling assumptions to find what the mass loss is of these stars. Because let's say 20 years ago, we thought that these mass loss rates were higher, but then when we included more physics, such as the clumping in these winds, we found actually the mass that these stars lose is lower than what we first observed. So in this sense, it's good to have both the simulations and the observations so that we can approach it from a physical and from an observed direction.
Yeah, thank you.
Thank you.
So, I don't have more questions either. But perhaps there are questions from the public. It's your chance. Let's go your. Yeah.
I have a question, sorry. I'm curious about the lack of divisibility jump. And it's not just a jump by you don't have like a change in the slope or anything. There doesn't seem to be anything happening. So do you have a single explanation as to why Göring found it and you found a completely different thing?
So the question was about the bistability jump to see why we actually do not find any change in the massless rate at this temperature. So one thing is of course we what I showed was our recipe, which is a boiled down version of the results of our grid, which just shows a simple power law of the massless rate with temperature. So that by default gives us just one simple slope. If we would look at the massless rates separately, so not in this recipe, we see that at the bistability region, because also we have some more trouble converging the models, there seems to be a bit more scatter of the massless rates. Maybe if we would split up the recipes in hot and a cool side, there might be a small kink in this recipe. However, it's important that if we stay fully below the region, we still get our reduced mass loss without any change of or any jump, let's say. Thank you.
No more questions? Okay, then once again, we will now go to the deliberate. Ladies and gentlemen, dear colleagues, I will now proclaim the result of the deliberation by the examination committee appointed for a doctoral degree in science, astronomy, and astrophysics. Mr. Robin Björklund has presented to the faculty his PhD thesis on the topic radiation-driven mass loss and its effect on massive star evolution, in partial fulfillment of the requirements for the PhD in science, astronomy, and astrophysics. And he has defended his thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of Director KU Leuven, I confer upon Mr. Robin Björklund the degree of Doctor in Science, Astronomy, and Astrophysics. And I hereby close the session. Thank you. I would like to give the word to the supervisor. Please.
Now the camera is there. Yes, okay. Can I take off my mask now? And breathe again. Jaha Robin, vad ska jag säga nu? 4 år, en lång tid. Väldigt lång tid. But actually it's been more than a pleasure, I would say. And yeah, they say 4 years is a long time, and you know that we've been living with COVID, but I actually don't feel that at all. I feel like these 4 years have just flown by. So of course, congratulations. And you have a beautiful thesis, which I've expressed several times now, and which I think was conveyed here as well. And really impactful results as well within the community. Perhaps, yeah, we don't have to rely on Alex all the time now. As was pointed out, we will see. Yeah. So, yeah, as also mentioned by Connie, right? You showed some interesting computation, and I've even read on your LinkedIn that you're passionate about the computational aspects. And just to give perspectives into the models, I remember Robin's supervisor, that would be me, struggled probably when we started with this with 2 or 3 of these models to get them working, And then Robin found a way, and yeah, only in this thesis there are hundreds to thousands of them presented. And when you look into our database, I don't even know. I just go back. There are many. So you did a really, really excellent job there. Must say. In the beginning, you remember in year 1 when we also started, right? Yeah. You did your computations there as well, but perhaps not with the impactful results that we always had. And then suddenly you also came, okay, so yeah, I was giving a talk in Mexico. Okay, yeah, that's great. So Robin got to go to Mexico in the beginning of his PhD, but I just had to ask, okay, but what are we going to talk about? We don't really have any results. No, I take care of that. And actually, that's also one of Robin's good skills. We did have some results, of course. And he put together a really beautiful presentation there for his first conference talk in Mexico, based on only a few months of work there. So that's probably the first one I realized, okay, this Robin will be fun. Of course, I never got to go to Mexico, so I only know that they seemingly have a great wine tasting. Oh yeah, that's also what you have. Yeah, wine tasting in Mexico. What can possibly go bad? And also that I shouldn't make my analogy with the glass and the master's degree. That's also what I've learned from that. Now, of course, we have talked a lot about Robin's science here, but he has also done a lot of other things at the Institute, the Study Olympiade, done a really great job there. And as many of you already know here, he's a real volleyball aficionado. So he has been, I've heard a lot of great stories about your volleyball adventures with your colleagues. So I'm sure that a lot of people at the Institute will miss you in terms of that. Perhaps not me, though. Because one of the things is that I am also, we share our sports interest, but perhaps I like football just a tiny little bit more. And Robin was so good at collecting people to play volleyball with him that we struggled for years in pre-COVID times to get enough people to play football. So yeah, there always is. So in this sense, you know, I actually picked up in your thesis in that in this sense I can just paraquote yourself, Robin. You know, if you can reach it with your hand, you can reach it with your foot. Of course, the quote in Robin's thesis, which if you read it, really read, is that if you can reach it with your foot, you can reach it with your hands. We share the sport interest, but of course we share a lot of other things. Among that our origin. So we're not just here working at Karl Löwen. We're also both from Sweden. Vi är båda svenskar, Robin och jag. Så det delar vi också. Of course also there, Robin is from the south, I am from the north. It's not just a football volleyball thing. Here we have the north-south things, right? So complement each other very well there, I would say. And the south is indeed very nice. One thing we do have in the north, though, is, you know, we have great skiing places there. So I hope that at some point we get to do that. That would be really nice. And actually, I do know that, I needed to look at this because I heard about this, that you do like the skiing and that one can go up to northern Sweden. One can also go to St. Moritz in Switzerland to do those type of activities. But I should say that also in Jämtland, where I'm from, we have great Dralju, I think it was called. Just a shared piece of information for you. Yeah. In this sense, I should also tell you that Robin, he also actually helped me in a great way, because suddenly we decided that, okay, so now we should have our weekly meetings together, but we're going to have them in Dutch, in the Netherlands, instead of in English. So Robin is perhaps, you know, something that the fellow students there can relate to, is that he's the one probably here who can say literally that for 6 months he could actually say, I don't understand what my supervisor is saying. So considering that also, it makes it a great achievement that you were able to win. I must say. So with that, of course, I just want to congratulate you again. I've lost the most important one. And say that, the things is beautiful, and there might be more to come. We will see. But certainly show the others the way, the path, how you do it, how you should do it, and even though there might be more, of course. There will only be one first, so to speak. There will only be one number one, and that is for me. Congratulations, and thank you very much. And then finally, due to the Belgian host, you will have something arriving to you within a few days.
Thank you. Very kind words. I don't have a big speech prepared. I just want to take the time to thank you as well, John. You have been a very great mentor, very great supervisor, and you have provided me with some very good times in the past 4 years. You were very good help when I needed it, and you also gave me the time to do my own thing if I wanted to. When with me now leaving the institute, leaving astronomy, I still feel that our research group is in very good hands with you. We've had a great time together. I'm sorry about the football. So yes, so also thank you to the rest of the research group. You helped me a lot within this research. It would have not been possible without you. As well as the rest of IPS, of course, we've had a lot of great times just having coffee or having beers or having wine tasting in Mexico or all these other trips that we did. It was all amazing, all thanks to you. And of course, my friends and family, you have always showed me a lot of support, and this helped me through these times, also during COVID, which was not that obvious maybe, but it was all a great help and got me to where I am now. So thank you a lot for that. And I think now it's time for the most important part of the evening, where we go to have some drinks and some food at the reception. So thank you also for following online, whoever could not be here. And I will see you when in the next opportunity. And I will see you at the reception. Thank you.